and welcome back to Blockchain Fundamentals with Bill Laboon. Today, we're going to discuss proof of work and mining, and finally see what Bitcoin miners are actually doing. So if you recall back to our naive consensus protocol, when we first discussed a decentralized cryptocurrency system, our idea was that we would pick a node at random and allow them to add the transactions in the transactions pool, bundle them into a block, and add it to the ongoing blockchain. But we saw that there were a few problems with this. First, how do we pick a random node? We assumed that nodes were honest, which is not always a good assumption to make in the actual world. And finally, there was nothing at stake. There was no real incentive for somebody to operate only one node as opposed to many nodes, or to propose as many blocks or as few blocks as they actually wanted. There wasn't any incentive to be honest. And so we eventually were able to figure out a centralized way to get around this by having Scrooge create a blockchain for us and have that be the source of truth. But we really don't want to have a centralized blockchain. So in order to fix this, Satoshi Nakamoto, who had seen the previous attempts that all ended with centralization, thought about things slightly differently. We can't punish dishonest nodes in a system like this. But what if there was a way to incentivize being an honest node instead? So in the Bitcoin system, that incentive is in fact Bitcoins. It's baked into the protocol. By securing the network, by helping to produce blocks, and by doing it in an honest way, producers of blocks are actually rewarded with Bitcoins. These Bitcoins come to the miner of a block in two different ways. The first is called the block reward. This is where all Bitcoin come from. When a block is produced, some Bitcoin are produced out of thin air and given to anyone who mines that block. Theoretically, it could go to someone else if that block miner was feeling extremely generous. A second incentive is transaction fees. So we'll see that when users send Bitcoin to another user on the Bitcoin network, they will often include a transaction fee as an incentive for the miner to quickly include their transaction in the next block. Miners will be able to take these transaction fees and add them to their own account as a reward for mining that block. So when a miner is able to produce a valid block, they're going to be rewarded in two ways. That block, the Coinbase, the block reward, the reward for producing a block, as well as the transaction fees included in all transactions in that block. So the creator of a valid block, as I mentioned, they get a reward. As of this filming, that is 12.5 Bitcoin. When Bitcoin first started, that was 50 Bitcoin for every block. It halves every 210,000 blocks, which is about every 4 years. So in May of 2020, if you're watching this after then, you will see that block rewards are now 6.25 Bitcoin per produced block. In another 4 years after that, in 2024, it will be 3.25, etc. Halvening and halvening and halvening, as they say, up until the year 2140. An interesting thing about this block reward, the fact that it is produced in Bitcoins, means that the block reward is only going to be valid if it's on the long-term consensus branch. That is the main chain that others are following, which in turn means that other nodes have accepted it. So if you're building off of a different chain, off of a different fork, then others will not recognize any of these Bitcoin that you produced. So this is an incentive to make sure that you are cooperating with everyone to produce a single chain. If you start working as a miner and producing blocks on forks of the chain instead of the original chain, well, these Bitcoin that you produce, nobody else is going to recognize them because they were not produced on that longest chain. So this may not seem like a huge disincentive, since you can always just produce as many blocks as you want. But it turns out that creating blocks is very hard work. You don't want to waste it. If you spend thousands or perhaps tens or hundreds of thousands of dollars worth of electricity and hardware and equipment to produce a block, you want to make sure that you get something in return for it, namely bitcoins. Bitcoins that other people agree that you have. All Bitcoin come from block rewards. There is no other way to generate Bitcoin. As I mentioned, they will end in the year 2140. But since the number of Bitcoin produced with each block is going to be cut in half every 4 years or so, for much longer than that, the number of Bitcoin produced as part of block rewards is going to be quite insignificant. A few what we call Satoshis, or 100 millions of a Bitcoin, for years and years ahead of that. So nobody is going to be mining around the year 2140, right? Because they're not going to get a block reward, and they're going to have to do a lot of work in order to produce the blocks. So why would somebody mine if they weren't getting this block reward? Well, the other incentive mechanism that we have discussed, transaction fees, will then come into play. We already see this. In the early days of Bitcoin, often zero-fee transactions would get included into blocks, either by simply out of the kindness of the miners' hearts, or because having these transactions made it easier to produce a block. However, we've already seen now that transaction fees are almost a necessity in order to get into a block, your transaction into a block in any sort of reasonable time. So how do we do this? What's actually happening behind the scenes to offer these transaction fees to the miners? So basically, the creator of a transaction, and we'll discuss exactly how this works momentarily, gives themselves back change from an account whenever they send a transaction. And what they can do is decide to give themselves back a little bit less in change than they sent. So it's just like giving somebody a $10 bill for a $5 item and saying, keep the change. This missing Bitcoin can be claimed by the miner of a block. So this keep the change can actually be picked up by anyone who mines it. This is an incentive for anyone who might be looking to mine, looking for transactions to package into blocks to pick up. Since by packaging this transaction, they'll get a little bit of extra Bitcoin in their pocket. So now it's time to dig in to how we can do that. And in order to discuss this, we really need to understand the central mechanism of how the Bitcoin ledger works. Because if I say that I'm going to send some Bitcoin to this particular address or this other address, I know what that address is at the time I create the transaction. If I want the miner to be able to pick it up, I don't know who that miner is going to be. It's completely decentralized. Some miner A may pick it up and my transaction and package it into a block, or miner B may do that. So how can we send Bitcoin to an address that we don't know? Well, in order to understand this, we need to understand UTXOs. So far, when we've been discussing Bitcoin and accounts and addresses, we've really thought of it, and I think this isn't a bad way to think about it, at least at a very high and abstract level, as some ledger where, all right, address X has 4 Bitcoin, address Y has 2.5, address Z has some other amount, just like a big spreadsheet. But really, each address has a collection of what are called unspent transaction outputs, or UTXOs. So these are transactions that have been input to an address, but not yet output to another. So when you try to determine how many Bitcoin or how much Bitcoin someone has in a particular address, really what you're going to do is tally up all of these unspent transaction outputs that were sent to a particular address. I think this is one of those things where if we see some graphics, it will make much more sense. So UTXOs go through transactions. They are outputs to a transaction. A transaction is just sending some transaction output that has not yet been spent to some other address. So in this example, we see a transaction TX0 where 1 Bitcoin comes in and one is sent to 2 different addresses. 0.4 of that UTXO, that 1 Bitcoin UTXO, goes to another transaction, and a 0.6 goes to a different address. So now, instead of one Bitcoin UTXO, we have a 0.4 Bitcoin UTXO and a 0.6 Bitcoin UTXO. Every time a UTXO is used, it must be completely consumed by the transaction. So we'll always end up with a UTXO being split or merged into other UTXOs. Every time we use a UTXO, it will be entirely used. We can't say, I'm going to take a little bit of this UTXO. We need to have it consumed completely. So if I just want to send 4/10 of a Bitcoin to somebody, what can I do? Well, at a very simple level, if I have a 1 Bitcoin UTXO, remember I have to completely consume that. So what I can do is send that to a transaction and have 2 outputs. The 0.4 Bitcoin goes to the intended recipient of the transaction, and 0.6 Bitcoin goes back to me. It could go back even to my same address. This is the change. So here is how we can end up by having a transaction that has less of an amount of any of our UTXOs, but we don't lose anything in the process. So here we've gotten back our 0.6 Bitcoin simply by having one transaction output just send it back to the initial address. We can do this in more complicated ways if we have multiple UTXOs with an account. So here, for instance, I'm sending 0.4 Bitcoin, once again, to some recipient. I have 3 UTXOs, 0.3, 0.35, and 0.35 Bitcoin. So I have 1 Bitcoin altogether, but in this case, it is split amongst multiple UTXOs. So what I can do, I don't need that last UTXO, but I take the first 2, the 0.3 and the 0.35, and I include both of those as part of a transaction. 0.4 Bitcoin goes out of the transaction, and 0.25 is returned to me. So now, instead of having a 0.3 and 2 0.35 UTXOs, I have that remaining 0.35 UTXO and my 0.25 UTXO, which will give me still a total of 0.6 Bitcoin in UTXOs, and the intended recipient still gets 0.4 Bitcoin as their UTXO. So this is just that same description, only I have highlighted the UTXO that go to the UTXOs that go to the intended recipient. Now, most Bitcoin wallets won't let you see in this much detail, or they will, but you really have to dig. They'll just say that your address has this much Bitcoin altogether. They'll automatically sum up all of the UTXOs associated with that address. Some Bitcoin wallets, and probably most Bitcoin wallets today, actually can have you have multiple addresses related together to help improve security and anonymity. They won't reuse addresses. You'll have multiple addresses that are all associated with the one account. And it can show you the collection of UTXOs for all of your accounts, all of your addresses in one account. So this gets us back to our original question. How can we give transaction fees to somebody that we don't know what their address is? So in this instance, I have a 0.4, I want to send a 0.4 Bitcoin transaction to somebody. And I want to provide a 1/10 of a Bitcoin transaction fee to entice miners, incentivize miners to include my transaction quickly. Again, you can imagine that a high transaction fee means that miners are going to be much more likely to try to include your transaction in a block in the very near future. And we see this actually when you have a very small transaction fee. A miner may not pick up your transaction for a long time, perhaps even hours or days. Whereas if you have an extremely high transaction fee set for a transaction, miners are going to be falling all over themselves to make sure that they are the one who get it in their block and are going to work as quickly as possible to get it onto the blockchain. Just like the postal system, if you want to get something done fast, if you want to send mail overnight, it's going to be much cheaper than if you send it third class to wherever. Similarly, in Bitcoin, if you want to have your transactions included in a block soon, you will need to probably pay a little bit more. Although probably not 1/10 of a Bitcoin, which is at the time I speak is about $700. That's a very high transaction fee. But just to make the math easy, let's continue with it. So here, I'm going to send a 4/10 of a Bitcoin to some recipient. But instead of giving myself back all of the change, 0.25 Bitcoin, I'm going to reduce that transaction to just 0.15 Bitcoin. Now, transactions, remember, must always completely consume the UTXO. So this UTXO, when it goes through the transaction, it's missing 0.1 Bitcoin. So what the miner can do is claim any of this leftover Bitcoin. So because I never said who this 0.1 Bitcoin was going to, which address, the creator of the block can take that 1.1 Bitcoin and send it to their own account. So now this 0.1 Bitcoin, after it gets put in the block, it's going to go to the miner's account. All else being equal, miners are going to want to have transactions with higher fees. So you can imagine, as I already mentioned, if you turn up the size of the transaction fee, increase it, miners will be more likely to put your transaction in a block much more quickly. Another way of thinking of this, besides the postal metaphor, is bidding for space. If you think about this as you are bidding for space in a block, which is of limited size. A block in Bitcoin can't have an infinite number of transactions. There's only a limited amount of space. And so just like if you go to ask somebody to rent an apartment and you're willing to pay $1,000 a month and somebody else is willing to pay $500 a month, the landlord is much more likely to let the $1,000 a month person rent the apartment. As of today, Bitcoin fees for on average for getting into the next block after they've been submitted was about 36 cents. If you don't care if it's in the next hour or two, that goes down to about 13 cents on average. The price for including something in including a transaction in a Bitcoin block varies very dramatically. So as I've already mentioned, especially in the early days, people often would have zero transaction fee transactions included in blocks. During the height of the crypto mania in late 2017, this would cost on average about $50 to put a transaction in a block. So as you can see, it really varies dramatically. Now, we'll discuss this a little bit later in the course, but there have been a lot of additional technologies added that have helped sort of ease the load on the Bitcoin blockchain, which can by itself usually handle about 3 to 7 transactions per second in total. However, which is one of the reasons why when it got very clogged, if you will, it became much more expensive to purchase space. It became the equivalent of San Francisco or some other place with a real estate boom. And now, however, because there have been, if you will, as an analogy, like mass transportation, other ways of moving Bitcoin besides directly on the blockchain, the fees have gone down pretty dramatically as of late 2019. So you decided that you would like to get into on this. What's to stop you from going out and making a block yourself, and then you get all those sweet transaction fees as well as a block reward? So nothing. You can do this at home. You can try to do it on your own computer. There are even some people that have tried to do this by hand. So nothing stops you. However, note there is a big, big asterisk next to that nothing. That is nothing that is stopping you. Because it turns out that you need to produce a valid block. And producing a valid block is going to require a lot of work. So this is a tax on identity. If you remember Sybil attacks, where we had Sybil, our adversary, generating lots of nodes that could then outvote any of the honest nodes on the network, proof of work is a way of resisting this. Because to produce a block is going to require a lot of external work that you simply cannot get around. So if you'll recall, Bitcoin uses SHA-256 hashes, and it uses these in a puzzle way. So when you're generating a block, you're looking for a block that meets certain requirements. So what you want to do is find a block with a nonce. Nonce is short for number used once, such that a hash of the concatenation of the nonce, the hash of the previous block, and all transactions in the block is less than some target. So in other words, we're looking for some string, which represents the block, and that's going to include the previous hash of the previous block. So this is sort of like a hash pointer, along with all of the transactions and other metadata necessary. And you want this to be less than some target. This target is actually going to be modified. It's going to be self-modified, actually, so that the more miners, the more hash power, as we say, is put at this, the number of blocks generated, or the time between blocks generated, remains the same at about once on average every 10 minutes. So in order to do this, remember some of the properties that we wanted for a cryptographic hash. And one was that it was puzzle friendly. That is, if we're trying to solve for the hash of some whatever value, the only possible way to do that is to generate that hash. There are no shortcuts to creating the hash. In other words, assuming some non-trivial target like max int, the maximum size of that, where we generate something that is just the same size as a hash, sort of a trivial way of doing it. We're going to have to try a large number of nonces. We're going to have to try a large number of modifications to the rest of the block so that the hash of that whole set is less than the target. Okay? And trying different values is the only way to do so. There is no shortcut. There's no concept of, oh, I got really close this time. I just need to modify X, Y, and Z, and I'll have it. The only way to try to get a new block is to simply calculate the hash again, which means that miners are calculating lots and lots of hashes as they move the block data and the nonce around. So for a hash puzzle, for something for proof of work, we want a couple of different properties to be to consist of. First, it should be difficult to compute. That is, there is a real Sybil tax that there are going to, if you want to generate a block, you're going to have to do real work. It's parameterizable. That means that the cost of this can be adjusted. We'll see when we look at one of the later Bitcoin blocks compared to the Genesis block that the difficulty has increased, in order to create a block by about 9 orders of magnitude. If we were not able to parameterize this cost, if we weren't able to adjust it, then as more hash power, as more miners, and if more powerful hardware has been put at the problem, what we would see is quicker and quicker block production. However, if we want to maintain consistently timed block production, then we really need to make sure that the hash puzzle we're using to provide proof of work for these blocks is adjustable as the amount of computing power goes up or down. Finally, it should be trivial to verify. Since all of the nodes on the network, even those who aren't mining, should be able to verify that the block was valid. So, difficult to compute, trivial to verify, and parameterizable. So, as I mentioned, we want people to prove that they have worked for this. We don't want this nothing at stake problem where anyone can say that, oh, try to look at my block and see if it's valid. It should be trivial to verify, but very difficult to compute. Okay? As the creation of this slide, when I just looked at the network estimates, miners around the world are looking at approximately 100,497,493 terahashes every second. That is, they are trying different nonces, different transaction configurations, putting the transactions in different orders, maybe changing the timestamp by a second or two, every second, over 100 quintillion times. So a terahash is a trillion hashes per second. Even with that, 100 quintillion times per second, a hash is being checked to see, a hash of a block is being checked to see, is this a valid block? And even with this, the immense amount of computing power, they generally don't find a solution until after about 10 minutes of this. So think about that. Every second, 100 quintillion possible blocks are checked. And it takes on average 10 minutes of that before a block is considered valid. So this number, this over 100 quintillion, you'll hear this referred to as the hash rate or hash power of the Bitcoin network. This hash power protects the network because if somebody were trying to create an alternate chain, they would need to have at least this much hash power behind them, which is, again, an immense amount of hash power. This is not something that an individual computer can do. It's not even something that an individual supercomputer can do. We'll talk more about what kinds of hardware are used to mine Bitcoin a little bit later. However, usually, if you were going to mine Bitcoin, you will be using specialized hardware, and all it really can do is try to generate Bitcoin blocks. So recall I had mentioned earlier about parameterizable cost. So best guess on what the hash rate was at, when the Bitcoin network started in early 2009 was about 4.5 million or 4.5 mega hashes per second. Again, this is orders of magnitude lower than it is today. But even in the early days, blocks were still generated on average about once every 10 minutes. So how does this work? Why does solving what is essentially the same algorithm 4.5 million times per second or 100 quintillion times per second, how can we still come up with a solution every 10 minutes under both cases? Well, remember that what we are looking for is that the hash must remain under the target. But we can modify what that target is. And the Bitcoin network actually self-adjusts every 2016 blocks based on how long blocks are being taken to produce. If blocks are taking longer than 10 minutes, then that target and thus the difficulty are adjusted down. So that the target is increased, which means that we're more likely to find some hash value that is less than that target. If the target is greater, it's easier to find something that's less than it. Conversely, if blocks are taking less than 10 minutes, it means that we have too much hash power and need to lower the target and thus increase the difficulty. Think of a dartboard. If not many people are hitting the bullseye, you might make the bullseye bigger. If a lot of people are hitting the bullseye and hitting it quickly, you might make it smaller. You want it to, in order to keep the difficulty the same, even though it's the same algorithm as throwing darts. So, as I mentioned, solving hash values is probabilistic. You never know when a block is going to be produced. Since this is on average, some miner could get lucky and find a block with the first try that they do, or within a few seconds. Other times it may take hours. So the average is 10 minutes. But you'll see that some blocks are produced in a very, very short amount of time. And in fact, most blocks are produced in less than 10 minutes, even though the average is still 10 minutes. Some blocks can take a very long time, even hours. However, on average, it's about 10 minutes. Well, I want to dig a little bit deeper into what I say when I say an average. I've been throwing that term around pretty informally, and I think we should really discuss a little bit about the timing. And so in order to do that, we need to understand what a Bernoulli trial is. So a Bernoulli trial is some process with two possible outcomes: true, false, success, failure, etc. And the probability of being successful is fixed between trials. So the probability never changes. It isn't that under some circumstances you've got a 50-50 shot, other circumstances you have a 75-25 shot. This the probability is is fixed. So the classic example of this is a coin flip, right? Every time you flip a coin, you basically have a 50-50, or at least very close to 50-50 chance of getting heads or tails. And if I just got heads, that doesn't influence the fact, whether or not I'll flip heads again. The fact that I flip 3 heads in a row doesn't mean that I'll get heads a fourth time, or that I'm more likely to get tails. It's the classic gambler's fallacy that some number is due. They are entirely independent trials. So in mining, we can think of this as a kind of Bernoulli trial, where success is that the hash is less than the target, and failure means that the hash is greater than or equal to the target. Now, if you take a single Bernoulli trial and iterate it to a very large number of values, so large that we can generally consider this a continuous instead of a discrete function, this represents a Poisson process. A Poisson process is a probabilistic process where events occur independently at a constant average rate. So, just like with flipping a coin, where getting 3 heads in a row, let's say that's the something successful, it's going to happen at a constant average rate. You'll get it every n seconds or n iterations. You'll get these. You'll get 3 in a row on average. That doesn't mean that it's going to follow a standard Gaussian bell curve. It doesn't mean that, it's been 5 hours since I've gotten one of 3 heads in a row, and thus I'm more likely to get 3 heads in a row. So this is exactly how Bitcoin works. The likelihood of a block is going to follow not a Gaussian distribution, but rather an exponential distribution. So if we look at an example here, so this is a theoretically derived curve of Bitcoin block production times. This is not empirical at all. This is just based on the math. So note that our graph is positively skewed. That is, the median is less than the mean. So the median time, the most the middle time, if we had put this all next to each other, is actually less than what the mean is. The mean is 10 minutes, but you'll see that there are actually more blocks being produced under 10 minutes than over 10 minutes. However, some of these long tail block times really impact the mean and sort of drag it out very, very far. So even I have seen block times myself of an hour or close to an hour, and especially in the early days of Bitcoin, you would see some very, very long times in between blocks. So let's step back and think what this means for us as users of the Bitcoin network. All right. So at the very beginning, no nonces have been tried. No one has done any hashing whatsoever. What is the mean time until the hash is less than the target? It's 10 minutes. Okay. However, now let's think 500 quintillion nonces have been tried. So many different values have been tried. We've rearranged blocks quite often. What is the mean time until h is less than target? It's still 10 minutes. So you always have, on average, 10 minutes to wait as a mean time. Because remember, all of these processes are independent. Just like if I flip coins heads 3 times in a row, that doesn't mean that I'm more likely to get tails. Just because 500 quintillion block configurations have failed, that does not mean that the next one is more likely. It's just like with dice. I just rolled 1. How many rolls on average until I roll a 6? Or I just rolled a whole bunch of numbers without a 6. It's still going to be on average 1 out of every 6 rolls will be a 6. There's no concept in a Poisson process of history. Each iteration is independent. So if you've been waiting half an hour for a Bitcoin block, the mean time to wait is going to be 10 minutes. If a new Bitcoin block was just formed, the mean time to wait is going to be 10 minutes. It's quite an interesting property of Poisson processes and a little bit counterintuitive. But just remember that at any point in time, the mean time for a new Bitcoin block is about 10 minutes. So, Bernoulli Trials, they have no memory. They're always 10 minutes away, no matter what. So you may think, well, I don't care about how long it takes the network to find a block. I want to know how long is it going to take me to find a block if I'm a miner? How soon until I can cash in on those sweet block rewards? Well, it's a very easy algorithm to figure out when you will be able to produce a block. So the mean time to the next block that you produce is 10 minutes divided by the fraction of hash power that you control. So if you control a very small amount of hash power, it's going to be a very long time before you yourself can create a block. If you own all of the hash power, conversely, well, the fraction of hash power you control is 1, and so you will produce a block on average every 10 minutes. If you control half the hash power, well, that's 10 divided by 0.5, so on average every 20 minutes, etc. Okay, so our last part of Bitcoin mining, we want to make sure that the puzzle we used is trivial to verify. Remember that it should be very difficult to mine a block, but easy for others to verify if it's valid. So it turns out calculating a hash is relatively computationally simple. All we do is run the SHA-256 hash function against the block that was produced. If the value is less than the target, then the block is valid. So compared to the miners who had to try hundreds of billions, trillions, quadrillions, quintillions of different input values, all you have to do as somebody trying to verify that they produced a valid block is run 1. So the amount of computational power you need to verify the Bitcoin blockchain is orders and orders of magnitude less than the computational power needed to actually produce it. This allows people to run Bitcoin nodes and verify that the network is working correctly, even if they're not the ones doing the mining. So, should you mine Bitcoin? Well, remember that your mining reward is the block reward plus transaction fees. Your cost is going to be your initial hardware costs plus ongoing operating costs, which are at the low end, if you're just doing this yourself, mostly electricity. Perhaps also systems administrators, etc., if you are running it on a facility. If the mining reward is greater than the mining cost, then yes, you should mine. It is profitable for you to mine. Otherwise, no, it is not profitable. That doesn't mean that you shouldn't mine Bitcoin or some other cryptocurrency. However, it most likely won't be profitable. There may be other reasons you want to do it, to perhaps understand better how mining works, or simply because you have a bunch of electricity you don't know what to do with. But generally, you should probably, before you get into mining, determine if it will actually be profitable for you. Unless you have access to cheap electricity, this is probably not the case. So this is a general overview of how mining works. And recall that one of the reasons that we have miners is decentralization. Mining is going to allow us to do something like Scrooge did with our Scrooge coin, but in a very distributed way. Right? Instead of having one single Scrooge, you're going to have anyone using the network and is mining, they all have the possibility of perhaps producing a block if they put enough work into it. But there is a problem here, something called a 51% attack. So what if more than half of the hash power is owned by a single entity? And this single entity might be malicious. Well, have we just has a Scrooge just emerged from the mists here? So our pseudo-Scrooge here can do some things against the network. However, not everything that Scrooge can do. There are still some benefits to decentralization, even if one entity owns much of the hash power. So can the pseudo-Scrooge steal coins? No. Remember, the only way to move coins is to know the secret key of the owner. Can our pseudo-Scrooge suppress transactions? Yes. So just like Scrooge, they could ignore transactions or by refusing to put them in blocks. Or if a chain is built with those transactions included, or blocks are produced with those transactions included, then the pseudo-Scrooge could decide not to build on those blocks. So they can suppress transactions. But there are ways around this. Since we don't have a single centralized entity controlling the blockchain, we do have transactions in mempools, the transaction pool. Remember, we send them around to all of the nodes, some of whom may be involved in mining and some not. At least you can realize that this attack is occurring. So there is transactions can be suppressed, but transactions cannot be suppressed silently. Can our pseudo-Scrooge change the block reward to give themselves 100 Bitcoin every block? No. They can't change the rules of consensus. The full Bitcoin nodes that are running, that are valid, that are actually following the rules, are going to ignore the blocks because they don't follow the rules of the Bitcoin network. Can they double spend? Yes. They can decide to build off a blockchain which doesn't include the block which had a sent transaction. And finally, and perhaps most damagingly, they can hurt confidence in Bitcoin, definitely. Since a key benefit of Bitcoin is its decentralized nature. So if you destroy this and try to make Bitcoin more centralized, then it's almost a self-destroying prophecy. by including reducing confidence in Bitcoin, whatever Bitcoin that they were able to get are probably going to be less valuable, as fewer people are going to want them. And so there's sort of a downward pressure on obtaining too much hash power because it will hurt confidence in the network. So our pseudo-Scrooge could do some things. However, not as much as our actual centralized Scrooge. The centralized Scrooge could change the block reward. That is, he could produce more coins than the network would initially allow. Suppress transactions without others realizing. Even perhaps change the rules of consensus. And our pseudo-Scrooge can't do any of this. Okay? So decentralization has benefits, even if there are entities in it that are trying to centralize. So this has been a brief overview of mining. In the next lecture, we're going to discuss more about the mechanics of Bitcoin. How are things actually done on the network, and what do these Bitcoin blocks actually look like?